हेलो से वेलकम टू आवर चैनल अगेन। टुडे हम लोग डिस्कस करने वाले हैं मिनिमम अनसर्टेनिटी कौन से वेव फंक्शन में होता है। यानी कि जो हम लोग यहाँ पे हाइजेनबर्ग्स का अनसर्टेनिटी प्रिंसिपल देख रहे हैं उसमें हमारा ग्रेटर दैन इक्वल टू एच बार डिवाइडेड बाई 2 होता है। तो हमें एक ऐसा वेव फंक्शन चाहिए जो कि मिनिमम अनसर्टेनिटी में हो, यानी कि हम पोजिशन और मोमेंटम को ऐसे कौन से वेव फंक्शन में मिनिमम अनसर्टेनिटी के साथ मेजर कर सकते हैं। उस वेव फंक्शन को हम लोग आज डिराइव करने जा रहे हैं और उसका जनरल सॉल्यूशन भी देखने वाले हैं। सो जनरली हमारे बहुत सारे ऐसे ऐसे वेव फंक्शंस होते हैं जिसमें कि हम लोग एक्यूरेटली मेजर नहीं कर सकते हैं पोजीशन मोमेंटम को, पर मिनिमम ऐसा कोई तो होगा जिसमें लोग मेजर कर सकते हैं, जो कि हम लोग स्क्वाच के इनइक्वालिटी थ्योरम से देखने जा रहे हैं। उनसे डिफरेंशियल इक्वेशंस को सॉल्व करके हम उस एक्सप्रेशन को लाने वाले हैं। सो दिस इज आवर टॉपिक ऑफ टुडेज वीडियो। सो लेट्स स्टार्ट आवर टुडेज वीडियो। First of all, we have to write down the squash inequality because the basic basis of this particular uncertainty principle is the squash inequality, which is like this: f inner product and g inner product is greater than equal to mod of inner product between f and g square. So this is our squash inequality. And one more important thing that we have discussed is that complex number whole square is equals to real part of z whole square plus imaginary part of z whole square, which is greater than equal to imaginary part of z square. So अगर हमें एक इनइक्वालिटीज की इक्वेशन को इक्वालिटी में लाना है तो हमें अपने इस पर्टिकुलर रियल पार्ट ऑफ z स्क्वायर को जीरो रखना पड़ेगा, तभी जाके हमारा ये इक्वेशन इक्वालिटी में बनेगा। सिमिलरली हम देखेंगे कि जो हमारा स्क्वाच इनइक्वालिटी होता है, अगर स्क्वाच इनइक्वालिटी में तो फंक्शंस हमारे हैं वन है एफ एंड जी। सो इफ एफ एंड जी के बीच में कुछ रिलेशन हो, विच इज if g is equal to some constant multiplied by f of x, then हमारा स्क्वाच इनइक्वालिटी इक्वल बदल जाएगा, ना कि ये इनइक्वालिटी रहेगा। इट मीन्स हमें इस इक्वेशन में एक ऐसा फंक्शन ढूंढना होगा जो कि जी एक्स के मल्टीपल में हो, या फिर इन दोनों के बीच में कोई रिलेशन हो, वेयर सी हेयर इज द प्योर इमेजिनरी नंबर। अब इसी बेसिस से हम लोग डिराइव करने वाले हैं हमारा वेव फंक्शन। हाउ? सो इफ यू रिमेंबर इन अ प्रीवियस वीडियो हाउ वी डिफाइन जी, सो जी इज नथिंग, it's our b minus expectation value of b, and here it's psi. And if you remember in our Heisenberg's uncertainty principle, b is nothing but it's just the momentum operator p. So we are going to substitute the value here. So what will happen is g is equal to momentum operator minus the expectation value of momentum, and here psi. Similarly, for f we have written a minus expectation value of a and psi. Similarly, a in our Heisenberg's uncertainty principle is nothing but it's the position operator. So now we are going to write down a as position operator minus expectation value of x psi. So this is our g and f. Now we are going to write down the equality equation between the g and f, which is g of x is equals to c, where c is the imaginary number. So we all know that c is imaginary number. Let's say we can say c is equals to ia, where a is some sort of real number while I is the imaginary path. Maybe the value of a can be 1, 2, etc. etc. So C and here fx. Now we are going to substitute the value of g and f. So g is nothing, it's the momentum operator minus the expectation value of momentum psi, and it is equals to c is iota a, f of x is x operator minus expectation value of x psi. So now we are going to write down the momentum operator formula, which is negative of iota h cut. We are going to not write this in partial derivative because our psi, the dependence of psi is only on x, not on the other functions. So we are going to write it d by dx. Negative expectation value of momentum psi, it is equals to iota a. The momentum operator x cap is x cap, no any difference, minus expectation value of x and psi. So this is our equation, and this is certainly a differential equation. So this is a very easy differential equation because only we have to do is a separation of variables, and after this we can easily find out the value of psi, which is our wave function for which the uncertainty is minimum. So let's see what will happen. First of all, be careful that this expectation value p and x, this are independent of x. Now this is, you have to remind this particular thing, and after this we are going to solve this. How can we write this equation? So let's see how we are going to solve it. Okay, first of all multiply it by psi. H cut d psi divided by dx, negative of expectation value of p psi, and it is equals to the iota a x cap psi minus x iota a psi. Now we are going to separate this particular term, going to shift this on right hand side and this expression to the left hand side, this expression to the left hand side. Let's see what will happen. We only have to separate the wave function and x. So here the equation will look like iota a expectation value of x, here it's psi, and it's negative of iota a x cap psi, and here it's negative of expectation value of momentum psi, and it's equal to iota h cut d psi by dx. Now take this particular iota h cut and dx in this on this left hand side and the psi to the right hand side by taking the psi common. So we can take the psi common. What will happen? Let's see. And putting iota h cut, let me first of all shift the dx and psi on the left hand side and the right hand side respectively. So what will happen? First of all, take psi common and taking dx on this side, it is iota a expectation value of x dx, first term, okay, negative of iota a x cap, which is the operator, and here dx, then negative of momentum operator dx, and it is equal to, closing bracket, yes, this is equal to iota h bar d psi. Now shifting psi on this particular side and iota h and left hand side, let's see what will happen. This expression will become iota a x dx divided by iota h cut, okay, and this will negative of iota a x operator dx divided by iota h cut, the negative of p, which is expectation value of p dx divided by iota h cut, and equals to d psi divided by psi. Now what we all have to do is to do the integration on both hand sides. So let's do the integration, 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 and integration. As I have said before, that here x operator and expectation value of x both are independent of dx. It means we have to take this particular term out of the integration sign. So our this expression become iota a x, okay, and it's iota h cut. The only term in the integration is dx, okay. Similarly, this will become negative iota a x operator divided by iota h cut integration of dx. Now here negative of momentum operator divided by iota h cut and integration of dx, and here it is integration of d psi divided by psi, which is equals to ln psi. Integration of dx is x. This will become iota a x and x divided by iota h cut, okay, negative of iota a x into x divided by iota h cut, and it's negative of momentum operator divided by iota, sorry, momentum divided by iota h cut x, and it is equals to ln psi. Now to remove psi, what we can do is that we can take e in this particular side and by, so here e to the power iota a x square divided, okay, so it is in power, let me write it in the TL letter. So here, so here it's e raised to the power iota a expectation value square, okay, and divided by iota h cut. It's all in the power, okay, negative of iota a x square, then expectation value divided by iota h cut. And negative of 1 over iota is negative iota, and this negative negative become positive. So this expression is iota expectation value of p x divided by h cut, and it's equal to the psi of x. Now if you remember that when I discussed about the variance, so in variance when psi square of some let's say function a, we are doing like this expression minus, so these are two different expression. Here, what we are going to do is that we are going to take the square of the A operator, then find out the expectation value of this. But in the second situation, what we are doing is that we are taking the expectation value of A, then we are going to do the square. And that's the difference. You have to find the difference between these two expressions are not equal. Let's say example momentum operator. What you are going to do according to this variance is that first of all you are going to take the square of the momentum operator, then finding out the expectation value, and in the second expression we have to find out the expectation value of p, and then we are going to square it. So how these two can be equal? That's why these two are not equal. Just like this, here you can see that here it's the expectation value square, and here is the square of the operator then the expectation value. So these two are the different things. So don't be confused that why we don't cut out these two particular terms. They are not same thing, they are different things. So if you have studied in Dirac notation how we represent the variance, it looks like this: x minus expectation value of x square. So this particular thing is exactly equal to this. This is exactly equal to this because at last when you do, it will become x square then expectation value, and it will be expectation value squared. So these two terms are different. So I hope you understand that why I'm not cutting these two particular terms. They are not same, they are different. Now what we have to do is that we are gonna transform our this particular thing, this particular expression into the same expression like this. If you have studied exponent, simple exponent rule, that ex plus y is equals to ex into ey. Just like this, I'm going to separate this particular term. So it will looks like this. Iota will cut out. It will become a expectation value square divided by h bar, and negative of iota will cut out a square of the expectation value, sorry, operator square divided by h cut, and here e to the power iota p operator x divided by h cut is equals to psi. Multiplication sign, it's power. Okay, then psi of x can be written as e to the power. What will happen if I take common this particular term, which is negative of a? Then what will happen is that this particular term will become the operator square expectation value minus expectation value of x square whole square divided by h bar into e to the power iota p x divided by h bar. So this is our wave function. Now we are going to modify some things. So this is our minimum uncertainty wave packet, and here we should add the amplitude. Sorry, normalization constant. So this is our minimum uncertainty relations. But here there is a calculation mistake, and I think I saw the differential equation wrong because the actual one has here 2 h cut. I think there's some sort of mistake here. So you can find out the mistake. Maybe I'm ending the video here. So the only mistake is I think I forgot to here. I think the differential equation, I will try to make another video where I solve this particular differential equation correctly because the 2 factor I think is missing here. So for now, thank you for watching my video, but actually this is our minimum uncertainty relationship. All the thing is correct, only the 2 factor is not there in our solution. I think by separation method we have done the some sort of silly errors. Okay, so for now, thank you for watching my video, and next video maybe is going to be on the mathematics of the quantum physics, which is the Dirac notation. And after this, we are going to start the series of the general relativity, not very advanced general relativity, but only the mathematics, like how we can do the differential geometry, because the differential geometry and tensors both are very lengthy branches. Differential geometry is very lengthy, and tensor, of course, is also very lengthy. So differential geometry and tensors, one video in a week maybe on these two topics are coming. So for today, thank you for watching my video.